Good morning. Welcome to this sixth lecture in this course of Advanced Computer Algebra. The fifth lecture, the previous video, was a bit out of sync with the storyline of this course. The main storyline of this course, at least in the first and the second part, is about efficiency of fundamental operations in computer algebra. We talked about multiplication and division, and we will now talk about other operations. And one other operation that will be the subject of today is evaluation and interpolation. And in the previous video, I recalled what you probably and hopefully learned in Computer Algebra 1, why evaluation and interpolation is so important. It's a general purpose technique for speeding up all sorts of computations that you may want to do in computer algebra. We looked at linear system solving, but that was mostly just an example. You can do more or less the same for any other, for almost any other computation that you can imagine. And we have seen that evaluation and interpolation is a general tool for avoiding the growth of expressions. So if you compute in a finite field instead of in the rationals, then there's no danger that things can go big, because every element in a finite field has the same size and occupies the same amount of memory in the computer. And it also means that the arithmetic in a finite field is not anything for which you have to worry about complexity, because every addition and multiplication in a finite field takes the same amount of time, so it's constant. Constant may be very big if you have a very big prime, but it's constant. So there's no expression growth, no expression swell in finite domains, and that's what we want to take advantage of by applying the principle of evaluation and interpolation, also called the technique of using homomorphic images, computing in homomorphic images. This is, as I've emphasized, it's a tool for speeding up computations and for fighting the general problem that we always have if we do symbolic computations. We don't have trouble with rounding errors and error propagation as we have in numerical analysis, where we compute with floating point numbers. We don't compute with floating point numbers in computer algebra. We compute with exact integers, and that's why we get exact answers. But there's a price to pay for this, and the price to pay for this is that these numbers can get very long. And that's partly unavoidable, because maybe the answer is just very long, but partly it is avoidable. It is avoidable insofar as we don't need to see the exact intermediate expressions, and which may be and often are much larger than the input and the output. And this is when the use of homomorphic images is extremely helpful in limiting the runtime, the computation time, to a reasonable amount. So what we didn't discuss last time was the cost. The cost of evaluation and interpolation. We just used it for making things fast, but we didn't discuss how fast the evaluation and the interpolation step themselves are. I've just mentioned towards the end that the classical algorithms need quadratic time. So that's like in the classical algorithm for multiplication. It also takes quadratic time, and that's not anything that we are happy with. We have to work to improve this, and this will be the topic of today. We will see how to get down from n squared to something better, both for evaluation and for interpolation. For evaluation, that seems a bit surprising that this is possible at all, because if you think you are evaluating at n distinct points, then the distinct points have nothing in common, so you probably have to do n times an evaluation at a single point, and an evaluation at a single point is linear time. So how much better can it be than linear time? If you have a polynomial that has a linear size, you'll have to look at every coefficient. There are linearly many, so you can probably not improve this. It's true, we cannot improve this, but nevertheless we can improve this even though the points are distinct and completely unrelated to another, to one another. We can take advantage of the fact that we are evaluating the same polynomial at all these endpoints, and we will see that this can be used. And for the interpolation, in the end, we have the same problem, that the standard algorithm takes quadratic time. Quadratic time is much, and we want to improve this as well. I've already pointed out that the classical complexities, like the ones that are stated here, they are based on the assumption that you are using the classical multiplication algorithm, which takes quadratic time. But this is not responsible for the quadratic cost here. So if you replace in the classical algorithms the standard multiplication by fast multiplication, you don't get any speed up here. You have to reorganize the computation so that fast multiplication can have an effect. And let me illustrate this on a different example, before we enter into the details of evaluation and interpolation. But yeah, okay, before this, let's just summarize what the task is, to be sure we're on the same page. And to fix notation, we are given a polynomial of degree less than n, and we are given n points in the ground field. We want to compute the values of the polynomial f at these n points. So that's a list of field elements again. That's the evaluation problem. And the interpolation problem, here we have given two vectors of length n, where in the first vector any two components are different from each other. The task is to construct the unique polynomial, that means the coefficients of this unique polynomial of degree less than n, which at every a has b as its value. Okay, this is the task. And we already have an evaluation and interpolation algorithm that is very fast, and that's the FFT algorithm that we discussed in the context of polynomial multiplication. But for the FFT algorithm, we got this speed by assuming a specific choice of evaluation points. Now, if you know that the evaluation points, or if you can choose the evaluation points yourself, then it's a good idea to choose roots of unity, powers of roots of unity, powers of a primitive root of unity, so that you can apply the FFT to solve the evaluation problem, and then you are done in n log n time, and that's great and works very well both in theory and in practice. But now the problem is different, because we assume that the evaluation points are now part of the input. So we have no control about them. We have no control over them. They are just given, and they may or may not be powers of roots of unity. And we want this process to be fast, even if they are not powers of roots of unity. Okay. So now let's go to an example that illustrates what goes wrong and why the use of fast multiplication does not automatically lead to an improvement. Let's see an example. So suppose you want to compute the product of n numbers. Let's say the numbers are small, they are between 1 and 100, and n is very big. You have lots of numbers, so probably the same number will occur several times, and the a's don't need to be distinct. I want to compute their product. So the natural idea for doing this is to compute the product one by one. So you take first a1, and then you multiply it with a2, then you take this result, multiply it with a3, and take this result, multiply by a4, and so on. So in the end, you have this product, and you multiply it by the last number, and then you get the final result. So this is 12. Numbers in this case, n is equal to 12. This is one option. But you have associativity of multiplication, so it's not necessary to do it in this order. You can do it also in the opposite order, but that won't make a lot of difference. But another thing you can do is to break the product in the middle and to do a balanced product. That's will of course lead to the same result. You can compute this product first, and then this product, and then compute the product of these two products. Now, how would you compute this product and this product? In the same way, you would split recursively. Say, okay, this product is computed by splitting it in the middle, and first compute this product, and then compute this product, and then multiply the two results together to get this box. Same here, and so on. So this is a general design principle for fast algorithms. Break the problem into equal sizes and not like here into something very big and something very small. We have actually already used this when we talked about Karatsuba. Karatsuba is also based on this idea of breaking the product in the middle into problems of half the size, rather than having something very small and very big like here. And also in the FFT, the approach was break the product into the FFT computation into two FFT computations of half the size. And this led to a speed up. Now we want to use the same idea here. And what difference does this make? Why is this better? So you can illustrate this as a picture. So this is a picture that would correspond to the first algorithm, where you compute this one by one. So you see here, you multiply the first numbers, you get the product of the first numbers multiplied by the third, get this result multiplied by the fourth, and so on. And you see that these big products here, they get larger and larger. It's indicated here by the color. Red is bad because it's a very long number. And you keep multiplying one by one, always a small number, which is restricted to the size, with a number that gets longer and longer during the process. So in the end, you have multiplied n numbers. You have performed n multiplications of something small with something not so small. In the beginning small, but eventually not so small anymore. And how big is this? Yeah, in the end it's size n. So if you have n numbers that all have a fixed size and you multiply them all together, and then you have a number that in the end is n times the fixed size. So this is a growth of the final output, the growth of the output. The size of the output grows linearly with the problem size n. So by the way, this means that here it's not a good idea to use homomorphic images for this problem, because here the output is the longest number that appears in the whole computation. So you're not going to save anything by using homomorphic images. You need something where in the beginning it's small and then it gets very large, and in the end it's like this, as we've seen last time. But here it doesn't help. Anyway, so the total complexity here is proportional to the area of this triangle, so it's quadratic. So you need quadratic time, and for getting quadratic time, you already assume that this multiplication here is that each of these multiplications takes linear time. And that's a justified assumption, because if you look at this, you have here a multiplication of something very long with something very small. And this doesn't take quadratic time. It takes linear time, because you just have, if you think that this is just a digit, then you have to multiply each of these digits with this digit, and then reorganize some carries. So you just have to think of polynomials, and this is a degree 0 polynomial, and this is a very long polynomial. Oh no, the degree so is not enough. Maybe degree 1 polynomial and a very long polynomial, and you just have to multiply the coefficients with each of these coefficients. That's 2 times n, and then add something up, which is also linear. So this is linear time. That means the quadratic cost of the standard multiplication algorithm is not responsible for the slowness of this evaluation procedure, of this product procedure. It's the wrong organization of the computation that is responsible. If we compare it with the other approach, then you get this picture, and you see already at first glance that this is much smaller. And what is happening here? Here we see the final result is the same as before. I've put it to a different scale. So this line here is this line here, which is much longer in this picture, so that we see a little bit more. How was this obtained? This line was obtained by one product of this half and this half. And this half in turn was obtained by the product of its two halves, and so on, all the way down to the original numbers. And since 12 here is not a power of 2, it doesn't fit evenly, and there's one that is a little bit longer than the others, which I have to split again, and that's why I have to do a recursion one a bit more, so it looks a bit funny in the shape. What matters is that in the end you still get the same result as before, which has n length, but the area of this shape is not quadratic anymore, because if you start by n and you keep dividing it into halves, then you're not going to get very far, because dividing into halves will lead to something of constant size already after a logarithmic number of steps. So the total area here is n log n. However, it is now not anymore justified to assume that the multiplication takes linear time, because here we have a multiplication of something long with something long, unlike before where we had a multiplication of something short with something long. So here this is linear time, and it's not an oversimplification to assume that this is linear time, it is really linear time. Here it's not linear time, so if you do this multiplication with the standard algorithm, it would take quadratic time, and you would have to account for this quadratic time in order to get a correct complexity analysis. That means you don't have any advantage doing it in a balanced way compared to doing it in the obvious way if you use the standard multiplication. Actually, it gets slower then, because you take here quadratic time times log, whereas this here is just quadratic time. So it's actually bad. It gets worse if you do it in this way with standard multiplication, with classical multiplication. But that's not what we want to do, of course. We want to use fast multiplication, and fast multiplication is fast. So here it's essentially linear time. So the picture here is quite appropriate, up to some logarithmic factors. So there's this logarithmic factor that says how many multiplications I have to do. But there's also the logarithmic factor that is part of the complexity of multiplication, or if you want, you can use the m function that we introduced. In any case, here you get with using fast multiplication, you get a speed up. You get an actual speed up that brings the complexity here down to something that is essentially linear. Okay, and this is something that happens very often. So we have seen this here in this, discussed this now in detail in this a very simple example, and I show you now how to do the same with evaluation and interpolation. So this is a general design principle that you can use to develop fast algorithms. The idea is We don't want to do a lot of small multiplications because we want to take advantage of fast multiplication. And to take advantage of fast multiplication, we have to trade many small multiplications for a few big ones. And if you have big multiplications, then you only then you notice the effect of the work that we have done in the first part of this course, where we reduced the cost for multiplication from quadratic to essentially linear. Okay, so this is the reorganization work that you will have to do when you design fast algorithms for computer algebra. And a good approach is always to split the problem in the middle, and we will see now for the evaluation and interpolation that this is an easy thing to do. The next video I'll show you a problem where we'll also gain something by splitting the problem in the middle, but it's not so obvious next time how to do it. Here it's still straightforward, so let's see how we can do it. Okay, so this looks a bit scary, but don't worry about this. This is it's just a complicated looking formula, but there's nothing special about it, nothing complicated about it. So we remember we had a polynomial, and the task was to evaluate this polynomial at a couple of numbers that we called a. And evaluating a polynomial is the same as taking the remainder of the polynomial modulo x minus the evaluation point. So let me introduce the notation mi for these polynomials by which I have to take do the division with remainder if I want to evaluate. And then these capital M's, they are defined as certain products of these small m's. So the product runs here from, okay, so this has two indices, I and j, and the product runs from this to this m, so it's a range of consecutive m's. Here we have a lot of these small m's from 0 to n minus 1, and n is very big. So there are lots of m's, and here I'll take a certain range, sub-range, an interval of this range and multiply them all up. So it goes from 0 to 2 to the I minus 1. I is the first index here, and then all the m's starting from this one up to this one plus this bound. Okay. So here's a picture. I hope this helps. So you arrange these m's in a tree. This is called a multiplication tree, where in the leaves you have the original small m's, and then you multiply two neighbors together to get the small m's are also the m's where I is equal to 0, because when I is equal to 0, then 2 to the 0 is 1 minus 1 is 0, so this would just be a product with a single factor. That means for m equals 0, for I equals 0, the capital M is just the small m. That's what we see here. It's the lowest level of the tree, and then the second index runs from 0 to 7 in this case, and that's just all the m's, in this case 8 m's. And then in the next level, so the first index is the level, the next level indicates, the next level contains things that are products of the things in the level above. So here you multiply the zeros and the first m to get this product of two m's. That's this capital M, and then these two to here, these two to here, these two to here, and this is the third m, starting from 0 going up to 3 makes 4 m's. Okay. And then in the next one, you multiply these ones together to get one of the m's, and you multiply these ones together to get one of the m's, so they are all together 2, and in the end, you multiply these ones together, and you get this m, and this m is actually the product of all the small m's. Okay, so that's a multiplication tree. The first thing I want to do is to compute all these capital M's. So the small m's I don't need to compute, I just can write them down. I've given the a's and I write x minus each of these a's, and that gives me the small m's. And I want to compute now these other polynomials that appear in the nodes of this tree. And of course they are bigger, and I don't want to keep them in factored form. I want to expand them. I want to see the coefficients of these polynomials. Okay, so this is relatively easy, because I can just compute them in the way how this tree is written. Also, if you wish, how they are defined. No, now they are defined like this product, but I use this idea of balanced product. So I compute this one out of those, and I compute this one out of those, and this product I don't compute one after the other, but I compute the product, of course, of this one and this one. And this one I obtain from multiplying these two together. So I construct this multiplication tree bottom up, where in this picture the bottom is on the top, and so in this picture it should be top down, I should say, from the leaves to the root. Okay, and I don't even need a recursion, because it's all very structured and regular. So you take the input data, the vector of length n, and we assume for simplicity that n is a power of 2. It's not a necessary assumption, but it's a simplification. And the output of the procedure should be the m's that are defined on the previous slide. Okay. So as I said in the beginning, for the leaves there's nothing to do. I just define what they are. I turn the input data, the evaluation points, into linear polynomials, and now I run over the levels of the tree from the first level above the leaves all the way up to the root, which is in the k's level. K is the exponent, 2 to the k is n. And then I compute each m in this level as a product of its two children in the tree. Okay, that's it. So what does this cost? It doesn't cost much. It costs altogether just multiplication time of n times log n many operations in k. So the correctness of the algorithm is hopefully obvious if you keep this picture of this tree in mind. What we should check is that it really has this announced complexity. So let's see. This is the picture from last time. So proof. Here we don't have a recursive algorithm. We really just have a loop, and the loop translates into a sum in the complexity. So the complexity, the number of field operations that this algorithm requires, if you apply it to an input of size n, is the cost of the outer loop, where k runs from 1, where I runs from 1 to k. So this is the loop here. The cost of this loop is determined by the inner loop, the cost of the inner loop. The cost of the inner loop is again a sum, and then we have here a multiplication. Okay, so we have here again a sum. Here j runs from 0 to 2 to the I minus 1 minus 1, and then we have m of whatever the degree is. Okay, but what is the degree? We can see this here in the tree. So at the beginning the degree is 1. Here on this level the polynomials were obtained by the product of two polynomials above. If they have degree 1, then this one will have degree 2. And this one will have degree 4, because either you say it's a product of 4 polynomials of degree 1, or it's the product of 2 polynomials of degree 2. Maybe the easiest way is to see it here, really. So these are polynomials of degree 1, and I'm taking a product of 2 to the I such polynomials, so the result is a polynomial of degree 2 to the I. Okay? Sure. So this is what I need here in order to see what is the cost of this multiplication. Actually, this multiplication is the only point in the algorithm where I'm doing something. The other thing is just things that either don't cost anything or that cost things that we don't count, like increasing the loop counter or so is nothing that we count. We count only field operations, and all the field operations happen in this multiplication here. Okay, so this is multiplication time of 2 to the I minus 1. Okay, but now we can use the assumptions that we have about the multiplication time to simplify this and estimate this to m of sum j from 0 to 2 to the k minus 2 to the I minus 1 minus 1, 2 to the I minus 1. And here, this is a geometric series. This is 2 to the k minus 1. And 2 to the k minus 1 is n half. So, altogether, this is the sum I from 1 to k. It's bounded by this. M of n half. Okay, but so this doesn't depend on I anymore. So this is really just k times m of n half, and k is log n. So altogether we are done. This is O of m of n. The half doesn't matter. It's eaten by the O, and then log n. That's what I claimed. Okay. So this is really as fast as I claimed. And now the question is, how can we use these m's to solve the evaluation problem? Okay, so let's see. Okay, let's see. The m's here, they contain several of these linear polynomials because they are defined as these products. And on the kth level, the mk will contain all of them, but the mk minus 1 will contain only the first half of them. It's the mk minus 1, 0, is defined as the product of the first half of these polynomials. So j running from 0 to n half minus 1. The second half will be the product, the product of the second half of these little m's here will make up the mk minus 1, 1 in the second index. So this is here. This is the mk minus 1, comma 0, and this is the mk minus 1, comma 1, and this is the mk 0. Okay, but let's look at the first half. If you consider the value of the polynomial that we want to evaluate at one of the evaluation points that belong to the first half, then you can do division with remainder with this polynomial here. So let's say q is the quotient and r is the remainder. And then since this x minus aj is a factor of this polynomial, this here will be 0. So this here doesn't matter, and we find that the value of f, the polynomial that we want to evaluate, at one of the first half of the evaluation points is equal to the value of this remainder. at the first half of the evaluation points. Okay, so this is 0. And for the second half, it's the same, just with the other polynomial. So the mk minus 1, 1 is the product of the second half of the lowercase m's, these ones, running from here to there. And so if you want to consider the value of f at one of these other evaluation points, the second half, then you can also take quotient and remainder, but with respect to the other m here. And then you find that this is 0 because j for this one is a root of this polynomial, just by the way this polynomial is defined. So this is 0, and we get that the value of f at this a is the same as the value of this remainder at this a. Okay. So we have reduced the problem of computing the values of f at the first half of the a's to computing the values of the remainder, this remainder at the first half of the a's. And for the second half of the a's, we can do the same, but just with a different remainder. Okay. So this gives the following algorithm, where the input is the polynomial that we want to evaluate, and it's assumed, as before, that its degree is less than n, and n is the power of 2. And then we have n evaluation points where we want to obtain the values of f. And we also assume that these capital M, these polynomials from before, have been prepared, and they are now part of the input. I've computed this multiplication tree, and I don't want to compute it again on the fly. I just want to store it somehow, somewhere, so that I can refer to the polynomials in its nodes. So here I regard it as part of the input, and the output is the value vector of f at all the a's. The idea is to do this recursively. Remember, we want to split the problem in the middle. That's what we are doing here. We split the value vector, or the evaluation point vector, in the middle, and recursively compute the values of the first half and the values of the second half, and the result is then just putting this together. So as in every recursive algorithm, you have a base case to take care of. That's when there's only one evaluation point, then you just evaluate your f at this evaluation point, and then you are happy. And otherwise, if the n is not 1, then you can compute these two remainders. So the two remainders, this is a one division, a division that of this polynomial of degree n by a polynomial of degree n half. Because here the product of these two m's is a polynomial of degree n. It's the polynomial of all the x minus a for all the a's, but this here is just the product of x minus a for the first half of the a's, and this is the product of the x minus a for the second half of the a's. So the degree of this m here is n half, and the same here. So I'm dividing here a polynomial of degree n by a polynomial of degree n half. So this will cost something. This is not for free. But here we are taking advantage of fast multiplication, or in fact of fast division. We know how to do this in a time that is proportional to the multiplication time. Okay, and then we apply this algorithm recursively, this one here, to compute the values of these remainders, for which we saw on the previous slide that their values are exactly the same as the values of f. So instead of computing the values of f, I can just as well compute the values of these remainders, provided that I take the right evaluation points. And and that's what I'm not doing here. Sorry for this. So here, this is correct. Here I'm taking the first half of the evaluation points, and here this is a typo. I should take the second half of the evaluation point. So here this should be a of n half all the way up to a n minus 1 when I evaluate the second polynomial at the second half of the evaluation point. So this comes back from the recursion, and here it's again wrong. Here is correct. I'm just attaching these two vectors of size n½ together. Here is the concatenation position, and I obtain the value vector of f for all the a's. This is how this works, and it's clearly correct. But what does it cost? It costs m of n log n operations in K. And why is this? So this is again something that we can easily see, prove. What is T of n? So now we have a recursive algorithm, and it does two recursive calls to problems of half the size. And then it does something in addition at every recursive level. And what it does in addition, as happening here at steps 2 and 3, it does two divisions with remainder. And I've already said that these are really not trivial divisions. They are divisions that are costly. And what they cost is the multiplication time, because we know how to divide as quickly as we can multiply. And therefore, this is O of m of n for steps 2 and 3, and finished. Because we have seen this recurrence before when we talked about fast division. Remember, I showed you two algorithms for fast division. The second one was the really fast one, based on Newton iteration, where we obtained a complexity that is exactly as fast as multiplication. But before this, I showed you a divide and conquer algorithm for division, which also breaks the division problem into two pieces of the same size, and then does a back multiplication, a bit like how we do it in hand calculation, but not digit by digit, but with a larger portion of the upper part of the thing by which you divide. Anyway, we had in this proof already this recurrence, and the solution of the recurrence, so from here it follows that Tn was O of m of n log n, and if this was correct before, then this is of course still correct now. The recurrence is exactly the same, and so also the reason is always the same why you get a fast algorithm, because it's always the same recurrence. Okay, so now we just have to put things together and get an algorithm for fast evaluation of a given polynomial at a given vector of evaluation points. The things that we have to do is, this is now just really putting things together. I have to do first, we have to compute these m's, because they are not just given, as I assume here. So I have to first compute them, and then I have to call this algorithm with the m's as input, and with this data as input. And we've seen that this first step takes m of n log n time, and the second step also takes m of n log n time. So altogether, this algorithm uses m of n log n time. And this is really good, and it's the best that we know. This is really good because m of n is essentially linear, log n is essentially constant, so this one is essentially linear. This means if you have a problem that is twice as big, then you have to expect that you need twice as much time, a little bit more than that because of the logarithms, but roughly doubling the problem size leads to doubling the computation time. So this is a good result, and this is all we need for evaluation. So for the evaluation problem is solved. We can do fast evaluation of a polynomial of degree n at n distinct points. What remains to be discussed now is the interpolation problem. So this is the backwards problem, where we are given the values of a polynomial, and we want to reconstruct from the values and the evaluation points the coefficients of the polynomial. Okay, we've seen last time interpolation is a form of Chinese remaindering for specific, first for polynomials instead of numbers, and then also for specific uh, um, moduli, x minus a's. And so you can either use Newton interpolation, which corresponds to the Chinese remainder algorithm, but you can also do Newton interpolation on symbolic input, and this then leads to this Lagrange interpolation formula that you have probably also seen already, which is based on the idea that you have certain basis functions that have the right values, that have somehow standardized values at the evaluation points, and then you take a suitable linear combination of them in order to get the polynomial that has values that you want at the evaluation point. So this polynomial here is designed in such a way that it is 1 when x is equal to aj, because then you have just on the top the same as on the bottom. And it is 0 at all the other a's, because there you have one factor in this product where you have ai minus ai. So here the product runs over all I, and j is the outer summation variable. So this here, as I said, this polynomial is 1 at this place, and it's 0 at all other places. So if you take the linear combination of these polynomials with the desired values bj as coefficients, then of course you get a polynomial f, which at aj has the value bj for every j, because the 0 doesn't disturb this, and the b multiplies with the 1. Okay. Now, of course, we cannot just compute the f according to this formula, because each of these products has size n, and we have to do n of these products. If we do this, we get quadratic time, and quadratic time is bad. We can also not use Newton's algorithm. Newton's algorithm would compute the same f, but not with this brutal formula, but more iteratively. But then we have the same phenomenon that we had with the triangle in the beginning today, when we computed the product of n numbers. This would be the effect in the Newton iteration. You will always combine something small with something big, and you do this very often, and in fact you do it too often. You do it n times, and in the last step it would take linear time. So altogether you get the area of the triangle, and it would be a quadratic algorithm. So we have to do something different. But starting from this Lagrange interpolation formula, we can get the m's back into business, because what you see here on the top is essentially almost the product of all the m's, of all the little m's. So remember, the little m's were x minus ai, and here you have the product of all of them with one exception. The j's is missing. So that's okay. I can just make this explicit. I can say, okay, this is mk0, so that's the product, that's the root of the multiplication tree, where all the m's are multiplied together, and I'm taking out the one that I have here too much. So this is the product of all of them, and this is the product of all except one. I'm dividing out the one that is not here but here, so I'm getting then the same result. And then the sj, for the sj, I take, I just introduce the notation sj for the product of all these denominators here. So sj is this one, and I have to divide it by this one also. So this here takes care of the polynomial part, and this takes care of the constant part that doesn't involve x. Okay. And then I can merge these two quantities together and call it C. And then what I have to do is really two things. First, I have to find a way to compute these S's. That's something we have to worry about, because the computation of a single s is takes linear time if I do it in the way as it's written here, because it's a product with n, or more precisely n minus 1 factors, but I have to do that n times. So if I do it according to the formula directly, naively, then that would be quadratic time, and we don't have so much time. That's one thing. And the other thing is that if I have these s's computed and then merge them with the b's to obtain the c's, then I have to find a way to compute these linear combinations efficiently. Okay, so let's see how we can do this. So first talk about the s's. This is the product that defines them, and now you need an idea how to get hold of these s's. And here's the idea. You take the polynomial here, the polynomial m, that is the product of all the x minus i's. That's the root of the multiplication t. And then you differentiate it. So it's a polynomial. You can differentiate it even if there's no calculus and no real numbers. You just formally differentiate it as you would always differentiate a polynomial. What do you get? So the m is, as I said, the product of n linear polynomials. If you differentiate it, you can use the product rule. And the product rule for n factors gives you a sum. This sum in which you have always, for every j, you have the derivative of the jth of these factors times all the other factors. So you get here the product of I different from j, so this looks already a bit like this here, and then you sum this all up. Okay. Now, how do we get the s here? We get the s, so that there's not just one s, there are n different s's. For every j there is an s, but we get the s's if we evaluate this polynomial here at aj, because if you put here aj, then one of these products will survive, and that's exactly the s that we need, which has aj here, and the product here, the one that is written here, runs over all I that are different from j. For all the other products that also appear in this sum, I don't have to worry, because they have a different j. So if I say here, maybe I compute the sk, and I would here put here the ak into the x, and then this would be 0, because the I runs over all indices that are different from j, and if the k is different from j, then one factor of this product will be ak minus ak. This is 0, so they all drop out. Only the one that we are interested in will survive. So this is good. It means that I can get a single s by evaluating this polynomial at the corresponding a. Now I don't want to have a single s, I want to have all of them. But that's something we can do. We just discussed how to do evaluation of a fixed polynomial at a number of different evaluation points quickly. So in order to get all the s's, all I have to do is apply the fast evaluation algorithm to this polynomial. And then I got all the s's. Okay? So the jth s, as I said, is the evaluation of the derivative at ij, and using fast multiple evaluation, I can get all of them at a very low cost. Cool. So this settles the first problem. And the second problem is now how to compute these linear combinations efficiently. So here's the algorithm for doing it. There's not much motivation needed. It's again a matter of splitting the sum in the middle, splitting the product in the middle. And I'm assuming here again that I have the product tree pre-computed and available for reference, so I can get it. Yeah, I can. Yeah, I have them available. So here the input otherwise is like for the interpolation problem of the interpolation points. Sorry, it's not the interpolation problem. It's this. Yeah, so it's this linear combination problem. I have the coefficients, the c's, and that's all I need. So it's a recursive procedure. If I'm in the base case, then there's nothing to do. I have here, and this would cancel out to 1. This m would be just x minus a1 divided by x minus 1 is 1. So the result is just, say, c0. And now I use that the the mk k0 is mk minus 1 0 times mk minus 1 1. So this is the product of all of them. This is the product of the first half, and this is the product of the second half. And now if you see the Cj, mk minus 1, no, k0 divided by x minus aj, j from 0 to n minus 1, then the question is, in which part of this m is this factor that I have to cancel out? So if you write this sum as sum j from 0 to n minus 1, cj, and then m k minus 1 0 times m k minus 1 1, and then there are two cases. Okay, now so let's first write it like this. You probably already see how it's going. In the first half of the j's runs through the whole range, but it first runs through the first half and then it runs through the second half. And in the first half, this factor is contained in this factor, and in the second half, it's contained in this factor. So I can say that this is the sum j from 0 to n half minus 1 cj, and then m k minus 1 0 divided by x minus aj times m k minus 1 1, and I can take this out because it doesn't depend on j anymore, and it's a polynomial. This is a polynomial, and this is also a polynomial because this denominator is contained in this small m. So this is the first half, and for the second half I can do the same. I can take out this factor here, get m k minus 1 0 times, and what remains is sum j from n half to n minus 1 cj m k minus 1 1. The product of the second half of the polynomials is 1 divided by x minus aj. Okay, so this is the idea of the algorithm. I can do this one recursively and this one recursively, and then I have to do this and this multiplication and this addition, which doesn't cost a lot. Okay, so this is what is happening here. I'm computing first this part recursively, and then this part recursively, and here I got it right without a typo. And then I do this combination here of where I add the missing factors. So you see, this is a problem of half the size, because decreasing k by 1 means you're going up in the tree, and you're going down in the tree if you write the tree in the usual way. So you're going to the children, and the children are always just half as big as their parents. Okay, so this is really a problem of the same form and also of half the size. Good. So this is correct, and we have the same recurrence as before. So we also have the same complexity as before. We have here t of n. T of n is equal to 2 times t of n half. The 2 comes from this and this, and the half comes from this being just half as big. And in addition, we have these two multiplications of size n. So this is again plus O of m of n. And since it's the same recurrence as before, it is also the same solution as before. And then we are done with this part, and we just have to plug things together and get the following fast interpolation algorithm. Interpolation algorithm now takes only the evaluation points and the desired values at these points as input. We assume again n as a power of 2. For simplicity, it's not necessary to assume this, but you get this. Yeah, just gets a little bit more complicated here if it's not a power of 2. The evaluation points are pairwise distinct, and the output is the unique polynomial of degree less than n, which at every a evaluates to the corresponding b. So the first thing you do is construct the multiplication tree. Of course, if you have a lot of interpolation problems to do with the same a's, then you will not compute a multiplication tree every time. The m's here depend only on a. So if you have a bunch of interpolation problems with the same a but varying b's, and you will save this step, do it only once for all of them, and then reuse it. That's the same remark applies, of course, also to the evaluation problem, where you may have different polynomials that you want to evaluate, but you evaluate them all at the same choice of evaluation points. In that case, you would also pre-compute these m's only once. But in general, somebody calls an interpolation procedure with any a's that you haven't seen before and any b's that you haven't seen before, and then you construct these m's, and it's not going to take a lot of time because we have seen this is also within the limits of what we are willing to spend at time. Then you compute the derivative of the polynomial in the root of the multiplication tree. And this is again an easy thing to do. This takes linear time. You just have to run through the coefficients and multiply them, shift them, and multiply them by something. So this is cheap. Now you compute the s's as the values of this g, this derivative, at all the a's. You can do this with fast evaluation. So this takes again m of n log n time. So we are still in business. And then you do this division that merges the s's into the b's. This takes linear time because it's just one operation for each of these n indices. This takes linear time. And now you call this algorithm 5, this subroutine here, that does this linear combination. And we have seen this is also m of n log n time. So everything here is at most m of n log n time, and therefore it is fast. So this is the fastest algorithm that we know for solving the interpolation problem. Okay, and now we are already at the end, because so this is the problem that we wanted to solve was fast evaluation and fast interpolation, and we have obtained algorithms for both of these operations that run in this complexity, and that's a good result. So just some final remarks about this. We have been assuming that we are working with polynomials over a field. That's not necessary. You can relax the coefficient domain to a ring, provided that you can perform the divisions that we needed to perform. and these were the divisions by the pairwise differences of the evaluation points. So if the pairwise differences of the evaluation points are invertible in the ring, then that's enough. Then you can use the ring as well. And actually, this generalizes this condition that we already had for K. In K, the only element that is not invertible is 0, and we assumed there that the A's are pairwise distinct. Yeah, that's this here's a, if you wish, a generalization or a relaxed version of this natural condition. Also, we have talked about polynomials today only, but there are also integer versions of these algorithms. As often, you can do many things that you can do for polynomials in the very same way also for integers. That's the same here. So you get an integer version of algorithm 4, which was the fast evaluation algorithm. And this means you have a very long integer and you have a bunch of primes and you want to compute the homomorphic image of the long integer for each of these primes. And you can do this fast, essentially in linear time. So the complexity there is m of n log n as well, but n is now the number of digits and m is the integer multiplication time. Okay, and the interpolation problem translates into the Chinese remainder algorithm. So the problem is again the same. You have maybe a bunch of primes and a bunch of homomorphic images. You want to reconstruct these homomorphic images to a pre-image, which is the correct modular, the product of the primes. And you can do this in the same way as we have discussed it here today for the interpolation problem for polynomials. And another point that is worth pointing out is that this speed up that we obtain crucially depends on the use of fast multiplication. So the results, as I stated them, remain true for classical multiplication because I formulated them for an arbitrary multiplication time. But you see, if you use classical multiplication, then you get n squared here, and then you actually make it worse because you get n squared log n, where Newton interpolation would just take n squared time. So don't combine this with slow multiplication. You really get the speed up only if you use fast multiplication inside of this algorithm. And you also see that the way how we achieve this is really, as I announced in the beginning, we have not really changed the way how we solve the interpolation problem. We haven't really gotten a different idea. The idea is still the same as in Newton interpolation. It's just that we have reordered we have restructured the computation so that instead of many small multiplications, we do few big multiplications, and this is advantageous if and only if you know how to multiply big things quickly. All right, so this much about fast multiplication, fast evaluation and interpolation. And now there is a little bit of time, so let's give a preview already on next time. Next time we will talk about greatest common divisor. This is, of course, an operation that doesn't require a lot of motivation. It's very essential and appears in many algorithms, and so it's natural that we want to have this also fast. And how can we make this fast? So I said that I wanted to show you two operations for which we can take advantage of fast multiplications. And the first one was evaluation and interpolation, where we saw that by splitting the problem in the middle, we can balance the sizes of the product, and that's good because then we get this famous now recurrence t of n is 2 times t of n half plus O of m of n, and this leads to a fast algorithm. But how can we do this with the greatest common divisor? Maybe we want to do it in the same way, but it's not so obvious how to do this. If you look at this, the task is to compute the GCD of two polynomials of degree at most n, and here's the Euclidean algorithm. I'm sure you're so familiar with this that I don't need to recall it, but let's have a look at this. The way how this works is you set h and h bar to f and g, the input polynomials, and then you have a while loop that runs for I don't know how long in advance. It runs until the second of these two polynomials is 0. So as long as it's not 0, I'm doing an update and replace h and h bar by h bar and this reminder. I don't know how long this takes, but if I know that it finishes some time because this gets smaller in every iteration and it cannot get smaller indefinitely often. So eventually, at some point, I will reach 0 here, and when I reach 0, then the other component is the GCD. This is the Euclidean algorithm, the way we learned it in Computer Algebra 1, or probably even before. And we also know that it takes quadratic time. And we are not happy with quadratic time, so we need to improve this. And if the idea is how to split the problem in the middle, well, then we are in trouble, because how can you here split the problem in the middle? So this is not so obvious. So let's see an example how this works. F and G are these polynomials here, and I'm calling them h and h bar for instantiation, and then I do division until nothing is left, and then this is the GCD. So you see at this picture already, this is a triangle similar to the triangle that we had at the beginning of today's video, where where we multiplied a bunch of numbers together, and the area of this triangle is quadratic, and so that's why this is a quadratic algorithm. You always have divisions, and they may be large. Here is a large division, but they usually are small, and if they are small, then you need many steps, but if they are large, then the division takes more time, so altogether you cannot escape. In the usual approach, you will spend quadratic time. And also in this example, if I write it down like this, it's not obvious how you could apply this idea of breaking the problem into even sizes, into two equal sizes, and apply somehow recursion, because we get these remainders only one after the other. So I cannot say one process starts here and the other starts here, because I don't know this until this one is finished. Okay, so let's have a closer look. I'll use, as usual, I'll use pictures to illustrate this, because the coefficients here, of course, don't matter. So this is what it looks like, the shape. You start with something big, and things get smaller during the process. You always keep divide until this is 0. And I'll call these remainders. So I call this these polynomials R0, R1, R2, R3, and so on. And in this example, the sixth one is 0, so the fifth one is GCD. But in general, you don't know this in advance. You can bound it, because you know in every step the degree decreases by at least once, but you see here it may decrease by more than that, and then you are finished earlier. So if you want to divide this in the middle, you don't even know where the middle is before you have done the computation. Okay, but let's see. Let's get even a step further and see how we can do this. So the zeroth remainder is one of the input polynomials, and the first remainder is the other one. And then each remainder, the ith remainder, is obtained by dividing the polynomial of 2 days ago by yesterday's polynomial. Okay, and this remainder also has a corresponding quotient. Let me put them into blue. Um, and then you have this relation that says the next one is the previous one minus q times the current one. Okay, and this you can write as a matrix vector multiplication. So you can say the pair that you consider during the Euclidean algorithm is obtained, is defined in this way. So this doesn't change here. But it's obtained from the previous one by multiplying the previous pair by this matrix. This matrix that contains here constantly 0, 1, and 1, and here minus the quotient of the current iteration. Okay, so this 0, 1 moves this one from the bottom to the top, and this 1 and minus q gives the linear combination of those that produces the next remainder. And if you keep going, and if you call this matrix Qi, then this one was also obtained from a previous one. So altogether, the product of all these Q's will turn the input polynomials f and g into the polynomials that you have in the ith iteration. Okay, and at the very end, you'll have a certain number of these q's, and I don't know in advance how big this number is, but you have a certain product of these q's and call this q, this product R. This is a matrix with it's a 2 by 2 matrix with polynomial entries. The polynomial entries are so that multiplying the matrix to the vector f and g gives you the GCD and 0. And actually, you'll have a little bit more because also the entries of the R are interesting. They are the cofactors that you compute in the extended Euclidean algorithm. They are in the first row of R, and in the second row of R, you get what is called the generator of the syzygy module of f and g. So it's also sometimes of interest, but usually more interesting is the first row of R. So now we have something that looks like we can divide it in the middle. And this will be the idea. The idea will be to obtain the H0 from the Fg by multiplying directly the R to it. That's something that we can do if we know the R. But how do we know the R? We will see that we can compute this product of the q's in a divide and conquer manner. So we will compute first the first half of this q's recursively somehow, and then we will do something and we compute the second half of this q's, and then the product of these two matrices will give the R. And the first half and the second half, this will be computed recursively. Okay, but how exactly we will do this? This is a bit tricky, and this is what I will show you in the next video. So for today is enough. Thanks for watching, and see you next time.